Alright, we're back, MECH2320, looking at chapter 35. We're going to talk a little bit about solid state DC motor controls. Okay, so we want to, understand what's kind of going on with them and, how are we able to limit the current control and, use everything to control the speed. Alright, so with DC motor controls, alright, they're used throughout industry. The induction motor is obviously the most common one, but that's not a DC motor. That one's AC. But there are a lot of applications that require DC motor controls. Okay, why? Because they can produce high torque at lower speeds. Okay, so high torque at lower speeds, and we have a lot of variable speed characteristics that we can use them. So we can control the speed very easily with DC motors, and it's another fact that we can operate the DC motor at or below its normal speed. Okay, so what that means is we're not using the full load voltage on it, and we're still going to get the torque that we need out of it. All right, so we operate it. You can fire it up at its rated voltage, or we can drop it down below, and it works below that. So that's good for us. Okay, we're getting that high torque, low speed, and we don't have to operate at full load voltage. Okay. Also with DC, our speed control is much smoother, and it's smoother because we're using separately excited control. So we're using separate power supplies when we do that. Okay, so this is kind of a look of how you're going to see, like on a schematic or power line, right? We can see where we have the field, okay, and we can see where we have the DC. So we're going to separately excite each one there. So one power supply is used to supply the constant voltage to the shunt field. All right, and the other one is going to variable, and it supplies voltage to the armature. All right, so we're going to use the two separate ones. So the bottom one is the one that's obviously going to the armature because we have A1, A2. Okay, so that way you can kind of distinguish which one's going to the field, which one's going to the armature. Field is obviously F1, F2. We're using this method to start. We've talked in previous chapters about using resistors to start and that sort of thing, but we don't want to use resistors in this case because there's a lot of heat that's lost through the resistor for these particular types of motor. So this is why we're going to use two separate power supplies as we go through these. Okay, so with that, okay, we use an excitation current to the shunt field, and remember, shunt still just means parallel. All right, and we usually generally leave that on even when the armature supply is off. That's kind of like it allows heat to still kind of be inside the motor casing, and that heat is actually used as a moisture deterrent. So that heat doesn't allow moisture to collect in there and keeps everything nice and dry and inoperable. Okay, so just some things to think out. How else it can help in that inside that enclosure, so we don't have any other issues. Okay. We use the armature power supply to provide a variable DC voltage to the armature. Okay, so a little bit different on that one, and it's considered, the heart of the solid state motor controller. So when we take a look at this, we want to understand, all the kind of different aspects that can go on with it as well. So we use rectifier diodes. Okay, so instead of using our normal diodes that we before, we use the SCRs, the silicon controlled rectifiers, to help produce our output voltage. Okay, so those are much better. It actually, remember, they take that full length and they cut it immediately in half, and that's where we're getting our DC out of this. Okay, so very important how we do that, and we can get a few amps up to hundreds of amps when we do this. So armature power supply, and very, very kind of crucial to what it goes on with this motor. Okay, we can kind of see when we look at the three-phase bridge rectifier that's going on. Remember, when we hear the word rectifier, I want you to always be thinking, all right, I'm going AC to DC. Anytime you hear rectifier, because that's its job. Okay, so we can look at the bottom left-hand picture there. Okay, we can see we have wavelengths 1, 2, and 3. Okay, it's coming off the three-phase Y there. And as we're feeding them through, all right, the diodes, normally they're diodes, right? But in this case, we're using the SCR, the rectifiers, okay? Notice how it cuts the wavelengths in half, and the way we're using all three wavelengths, it's actually producing our DC wave, okay? So, and then we do a few other things to help clean that wave out so it's a nice pulse, okay? But that's how our three-phase bridge rectifier is really working. And we talked a lot about that in the electrical class so that we can kind of understand, you know, the different aspects of these wavelengths and what really happens when we're rectifying, okay? But once again, all right, we're looking to control the voltage. That's what we're really essentially doing with this DC motor. We're controlling the voltage. Remember, affecting the field strength, not speed. Okay, so how do we control the voltage here? All right, we're doing the phase shift on the SCR. So remember the phase, we can look at, I'm stepping back a slide here. Remember when we talked about leading and lagging currents and voltages in the electrical class? So you can see that you know, C is actually leading A and A is leading B when we're looking at the wave diagram here, okay? So that's really what we're talking about when we're talking about leading and lagging, all right? And we're talking about phases, okay? What angle that's at what specific time, and how much it's leading and lagging by. So we can use it to shift the phases a little bit. That's how we're going to control our voltage, okay? So when we do that phase shift, that determines our output voltage that we get from that rectifier. So, you know, schematically we can take a look at it here. Notice there's a single diode, okay, that's going back across the armature there. What's that? That's called our kickback diode. And we use that to kill any inductive voltages produced in the armature. So we can limit the direction of it so we don't spike anything back through the system. Okay, so that's what that solo diode is that's next to the armature. Sorry, that's our field, that's our kickback, that's our filter. You know, just to make sure that if something does happen from that armature, that it's not going back and ruining our system. Okay, so we can also, you know, we have to have safety for these motors as well. So if something fails, we want it to be able to detect that fail and shut the motor down, okay? Because if the DC motors fail, they're kind of like your series motors. They will spin out of control if there's no load or anything else like that on them, okay? So we want to make sure that we always detect if the field fails, okay? If the field fails, okay, so we will have issues. So we can detect across the sensor and those sort of things. So we want to look at a couple different ways here of, you know, how we can detect that. Okay, so if we take a look here, all right, we have our rectifier, we have our phase shift control, so we can see how it would impact the phase shift. Okay, so if we take a look at the field failure control, if the field fails, okay, it tells the phase shift control that that's happened. Okay, ways we do that. All right, so we have limit the current to a safe value, so we can detect the current here in the line. So if the current isn't where we want it to be, we're able to control it, turn it off. Okay, but we're checking the current in the AC line. Okay, we want to take that signal, all right, and we can limit it as it goes to that phase shift control. So we have field failure in there, we got limit the current, all these different ways that we're protecting this DC motor, because like I said, if something happens to it and it goes out of control, it will destroy itself. Okay. So why use them though? All right, it's for speed control. They're that's really the greatest advantage of using a DC motor. All right, for speed control, we can change the speed, or we can maintain a specific speed very easily. Okay, even if the load's changed. So that's why they're very good. So like a load change, right? Or we put something on a conveyor, or those sort of things that impacts what's going on. We are able to read those impacts through, you know, current and fields and things like that, and detect changes and make it so that everything is going smoothly. Okay, so very common method of detecting motor speed with this is an electrotachometer. Now you guys used a tachometer in the mechanical class, right? You use that to you know, read the RPMs on the shaft of the motor as it was spinning. But in this case, all right, it's very, very similar, all right, but it's just a permanent magnet generator that's connected to the motor shaft, all right. So the voltage of the generator is proportional to its speed. So we're able to detect that and know, is it running correctly, and we're able to actually detect the speed of the motor using that. So where would that go, and how does that tie in, all right, in our operator control panel, right? So we're able to check current, check if the field failed. We're able to just read the speed. How fast is the motor going right now? What's the RPMs on the motor? So we're able to detect that. All right, and all that kind of goes into the phase control. So as all of these things are happening, the phase control is getting that and knowing what the adjustments need to be in order to make it sends it into the rectifier so that we're actually getting the motor doing what it needs to be doing and being at that constant speed, regardless of what's happening to it. So, just all these factors that come into play that we put onto the DC motor here when we're separately excited, and everything that kind of goes in and feeds that rectifier. So we can make changes on the fly, and it'll auto-detect and auto-correct as it's going. So that's kind of the cool part about using something that's a solid-state device, is it's kind of very self-sufficient. It's getting a closed-loop feedback system. It's getting information from the system, and based on the information that it's receiving, all right, it has the algorithm that it's going through, and you've designed so that it knows, all right, if this field fails, what do we do? If the current's not here, what do we do? All right, if the speed's not here, what do we do? We adjust the voltage accordingly. So just all those different things coming together, and the advantage of having like a solid state control. All right, guys, as usual, email me if you got any questions. Else, I will see you in class.